Okay, so now we're going to sort of complicate things a little bit and talk about alkanes with substituents. So these will be our branched alkanes, right? So previously we talked a lot about the straight chain. Now we're going to sort of complicate things a little bit by adding these branch points. Okay, yeah, so this is saying exactly that, right? So up until this point, we should be able to name this compound right here. What would that be? There are 4 carbons, so that's butane. What we don't know how to do, right, so that has the formula C4H10. What we don't know how to do is name this guy here. Notice that it still has the same formula. You can count everything up and convince yourself of that. But it has this branch point. So we're going to need to learn how to characterize that using its IUPAC name. There's going to be a set of rules that we're going to learn. And just like before, we're going to sort of start simple and then add on the complication as we go. Okay. First sort of bit of vocabulary that we want to learn here is this idea of a structural isomer. And these are molecules that have the same molecular formula, but a different arrangement of atoms, a different connection of atoms. So just like we saw, I guess that's the same example right here. Just as we saw here, these all have the formula C4H10, C4H10. So they have the same molecular formula, but they have a different arrangement of atoms. They have different, the bonding is not the same in that you have this carbon here that's bond to 3 different carbons, and you don't have anything like that in this particular straight chain above, right? So these two would be considered structural isomers of one another. The more carbons an alkane has, the more structural isomers there are. So this wants us to draw 3 possible structural isomers of pentane. So first, let's do the obvious one, right? And that is our straight chain here. Okay. What I'm going to do, you're going to notice as I'm doing this problem, I'm not going to worry about the hydrogens just yet, because what really makes a particular compound different is the connectivity of carbons. Hydrogens are just kind of there to decorate the outside and make sure that the carbon has a full octet. But there's never going to be different isomers that only differ by the placement of the hydrogens. Okay, they're always going to be sort of an afterthought, which is actually another reason why these bond line structures are nice. The position of the carbons are indicated by those endpoints and intersections, and then the hydrogens are just implied. You just figure out where they are based on completing carbon's octet rule. Okay, so I'm going to do the same thing here when I'm worrying about these different structural isomers. I'm not really going to worry about the hydrogens until after the fact. Okay, so how do I go about finding a different structural isomer? Well, kind of how I think about it is I'm going to start with what I had at the beginning, and then I'm going to pick up this carbon and move it somewhere else. So now I'm going to put it on that carbon there. Okay. That's another one. Okay. It might be tempting to say, well, let me pick up this one and now move it over here. These guys are actually the same thing. And this is something that's going to be a really big pain in the butt for you guys to see at first. But if you could just like take the mirror image of something and get the same thing back, it's the exact same molecule. What might be helpful is if you guys have one of those molecular modeling kits, one of these, like like they got the beads and you can kind of connect things together. That might be a great way to prove to yourself, because what you could do is build this model here, and you realize if you just picked it up and turned it over, you would get this one here. Okay, but these are both the same molecule, and being able to get to a point where you can see that is going to be kind of tricky, but that will be our goal throughout the semester. So this does not constitute, so these guys here are not structural isomers, they are identical, meaning they're just the exact same molecule, kind of drawn a different way. So if we want to get our other structural isomer, let's actually start here, and we're just going to take this guy and move it down here. All right, now, obviously I've been studying chemistry for, God, like 20 years if you count high school. Clearly, I'm pretty good at this. I know how to just look at something and do it. You guys might have to struggle with it a little bit more, and that is okay. That's what you're here to do. But you have to be putting pencil to paper. One of the things that I'm going to try to drill into your head throughout the semester here is that nobody ever learns chemistry by sitting there and listening to somebody else talk about it. It's all about grabbing your pencil, putting it to paper, and drawing all these different things, kind of looking at them and saying, is this the same or is it different, etc. Okay, so anyway, just to finish this off, these are going to be our 3 possible structural isomers. I can go ahead and draw them in their bond line formula as well. Actually, when you have a carbon that has 4 other carbons bound to it, we draw that. Usually we keep like these 120-degree type angles when we're drawing these structures. When we have a carbon with 4 bonds to it, you'll put it at a 90-degree angle. Okay, so this is just something you'll get used to. And then we can go in and make sure that we have all our hydrogens bound too. I'm going to be lazy and do a condensed structure sort of thing. And then notice that this carbon here, because it's already bound to 3 other carbons, should only get 1 hydrogen. Right? Likewise here, each one of these will get 3 hydrogens attached to it. And then how many hydrogens go on this central carbon? None, because it's already got 4 bonds. Right? So that's what I'm saying. The hydrogens are kind of an afterthought. You go in and fill those in after the fact. Okay, so these are 3 different structural isomers. They all have that same molecular formula, but different connectivity. Notice also, because we were, so because these were all single bond, I feel like the natural question might be, well, why didn't you have to worry about the number of hydrogens? Well, because I knew that there were all single bonds going on. We will complicate things a little bit in the future when we talk about alkenes and alkynes, but for right now, since we're just talking about alkanes and I know they're all single bonds, it's kind of going to be a given that I'll be able to just fill them in afterwards. And of course, you can double check, make sure that we indeed have 3 that will take us to 5, 7, 9, 12, and you can do that for all your structures to convince yourself at first. But you'll start to get a feel for as to why these sort of things are, and you'll be able to kind of just look at it and know that that's the case. That's what we're building towards. Okay, there are 2 types of substituents that we're going to talk about in this chapter. The first one are alkyl groups. So this would be something like, I have pentane. Actually, I'll do. Oops. Okay, and then a substituent means it's going to be coming off that main chain. So I'm going to erase one of these hydrogen bonds here and then stick on another hydrocarbon, right? So an alkyl group, notice that same root word as alkane. It's just a group that consists of carbons and hydrogens. Okay, they will have an -yle ending. So this guy right here would be a meth, because it's only 1 carbon, -yle group, right? So that substituent there is a methyl group. Okay, and again, we're going to use those same prefixes that we learned back in this table here. So we still have these same meanings. Flashcard this. You have to know this association. But if our substituent is 1 carbon, it's a methyl. A 2 carbon would be an ethyl. A 3 carbon would be a propyl. et cetera, et cetera. You just take this same prefix and instead of ane, stick the YL on the end. Okay. The other type of group substituent that we're going to talk about, because they're pretty easy, are halogen substituents, halo substituents. So these are any element that's sitting in that halogen column on the periodic table, specifically fluorine, chlorine, bromine, and iodine. And what we do was we kind of like abbreviate, I don't know if abbreviate's the right word, but instead of being fluorine, as a substituent, it would be fluoro. Chlorine would be chloro. Bromine would be bromo. And iodine would be iodo. So again, if I'm going to take this same sort of example here, but instead of having a methyl group, I were to stick something like, let's do bromine. As a substituent, this would be a bromo substituent. Okay. This is going to seem a little overwhelming at first. I'm going to be dead honest with you. Nomenclature was something that I hated when I was first doing organic chemistry. The good news is that you can just do a bunch of practice and then it will be second nature and then it's going to be super easy. And that's really the goal that I have for you guys, is to get to the point where you are just experts at nomenclature, because it is something that's really important. Okay, this is kind of the master cheat sheet table of all the different substituents that you're going to have to know. Flashcard this, but let's just go through. Some of them we sort of already know, and other ones are really weird, and we're going to have to kind of like just file them away as special things in our mind. But what do we call a substituent that's only one carbon? Right, use that prefix. What prefix should we be using for one carbon? This will be a methyl group. What about when there's two carbons? What will that substituent be called? This will be an ethyl group. When there's three carbons, and by that I notice how all three of these are kind of in a line here. So for example, let's do something like cyclohexane, and then I stick 1, 2, 3 carbons on there, all in a line. 1, 2, 3. That would be a propyl group. If I stuck another one on there so that it was 4 carbons, what do we use for 4 carbons? That would be a butyl group. Okay. Now, if I have 3 carbons, but notice that they're not all in a line. Like what this drawing is sort of conveying is that the way that they're connected to the molecule, here's the base of what we call the parent chain, or the larger molecule. So if I'm going to draw that on here, these 1, 2, 3 carbons correspond to these 1, 2, 3 carbons. So there's 3 carbons, but they're not in a straight line anymore. They're kind of in this fork. This has its own special name. It's unfortunate that we just have to sort of, again, file this away as something special in the back of our mind, but this would be called an isopropyl group. So isopropyl. Prop because we have 3 carbons, but the iso lets you know that there's that fork. Likewise, if we have, let's do our same cyclohexane base, but we have, again, this sort of is where the rest of the molecule is. We have 1, 2, 3, 4 carbons, but again, there's that fork at the end. So what this is telling, looks like on our structure would be something like this. Here's our 1, 2, 3, 4 carbons. This is isobutyl. So iso is, think fork at the end. Isopropyl means there's 3 carbons with a fork. Isobutyl means there's 4 carbons with the fork. So this is isobutyl. Okay, there are two other special 4-carbon ones we got to know. They also have their own weird names. This is 1, 2, 3, 4 carbons, but it's the second carbon that's bound to that parent chain, right? That's what that represents there. So let's just draw that out. What would that look like? Here it's the second carbon in the 4 carbons. And that is what we call a sec-butyl group. Notice that there's a dash between sec and butyl. Sec-butyl. And lastly, when we have a 4-carbon group, and again, here's where it's connected to the parent chain, but our middle carbon is bound to 1, 2, 3 other carbons. That is called a Tert butyl group. Okay, so if I were to draw that, that would be, this is where we have our right angle thing going on because we have a carbon bound to 4 other carbons. So 1, 2, 3, 4 carbons that make up a Tert butyl group. These 4, I think, you know, the methyl, the propyl, or methyl, ethyl, propyl, butyl, those are all kind of logical in that they fit in with the same naming scheme as the alkanes themselves do. These ones, I think, are the harder ones. These are kind of the special flashcard. We have to know them for the ACS exam. They will be on the ACS exam. But I do kind of keep them in a special place in my mind. Yeah, because they got their own little weird name here. But those are those different substituents. And then as we talked about with the halogens, fluorine becomes a fluoro group. Chlorine is a chloro group. Bromine is a bromo group. And iodine is an iodo group. Okay, these are the substituents of alkyl groups you guys need to know for this chapter. Okay, so then how do we go about naming something like this, right? That's going to be our goal that we're going to be working on. The next few slides actually sort of walk you through it a little bit. I'm going to do it all right here, so just listen and follow along with me. Okay. The first step that we have to do is find the parent chain. And that is the longest contiguous carbon chain. So the longest set of carbons that you can trace all the way through, right? The way that this is drawn, and that's going to be how our first few examples work, is they're drawn in a way that's going to make it kind of easy for us. You can see that the longest set of carbons is 1, 2, 3, 4, 5, right? Notice that I can't go 1, 2, 3, 4, and then jump back up here because this is not continuous. Also, I wouldn't want to just have 1, 2, 3, 4 be my longest set because it's not the longest. There's an even longer chain that I can choose, such as this one, 1, 2, 3, 4, 5. Okay, so when you're identifying your parent chain, you're trying to figure out the longest continuous set of carbons that exist. That's going to kind of make up the core of our name, the core of our molecule. Everything else is going to be considered a substituent, something that's branched off of there. Okay, so step 1 is find our parent chain. In this case, this group right here is going to be our parent chain, which means that this chlorine here and this methyl group here will be considered substituents. Right, so the parent chain is the core, everything else decorating it is the substituents. Notice how I'm basically ignoring the hydrogens. Okay, 2 is number your parent chain. Okay, so I'm going to go through and number this parent chain. This is going to be carbon 1, this is carbon 2, This is carbon 3, this is carbon 4, this is carbon 5. Step 3 is name your substituents. One of the things I kind of forgot to mention is we've got our parent chain, so we can actually name the parent chain portion. Because we have 5 carbons, this will be a pentane. Right, so pentane is going to be included in our name. That's going to be the last part. We also have these 2 other substituents. What do we call the chlorine? Remember, when chlorine is a substituent, it is a chloro. And what about this guy down here? It's a 1 carbon substituent. So that would make it a methyl, right? Remember, the meth corresponds to the fact that it's 1 carbon. The YL means that it's a substituent instead of a parent chain. Our parent chain gets that ANE ending. So now we got to combine all together. So the last step is to combine with the numbers. And we're going to put the substituents in alpha order. Okay, so when I'm building my name, I'm going to use these different components, the chloro, the methyl, and the pentane. Now I'm going to throw them together, and I'm going to make sure that my substituents are in alphabetical order, and it's going to end in pentane. So actually, I'm going to build it from back forward. Last is going to be pentane. If I'm going to put my substituents in alpha order, which one should come first? Chlorine should be before methyl, right? And then what I have to do is when I put them in there, I'm going to have to number the position that they're in. So this would be 2 chloro, 3 meth, and I didn't leave myself quite enough room. Methyl, pentane. Okay. So my methyl group is at position 3. That corresponds to this portion of the name. My chlorine group is at position 2, so that's accounted for in this portion of the name. And my parent chain in green is a pentane. So that's really what our goal is when we're naming our compounds using this IUPAC naming scheme, is that we account for every feature in this molecule within the name. Right? So given a name, you should be able to draw a molecule, a unique molecule that corresponds to it. There's no ambiguity with what's going on. So that's how we construct a name, is those 4 steps there, okay? Find the parent chain, then you can identify it. In this case, it was a pentane. Number that parent chain, name your substituents, and then put it all together with your substituents numbered in alpha order. Okay, so this kind of walks you through that process here. Okay, so now let's talk about when we're naming cycloalkanes. When you're naming cycloalkanes, that cycloalkane is the parent chain. Okay, so if I were to ask you to name this here, remember that first step is find the parent chain. This is our parent chain. Our parent chain is a cyclohexane. And that means that this is going to be the substituent. Remember, the next step is going to be to name, well, actually the second step is really to number our parent chain. When it comes to a cyclic compound, you just always start with number 1 at where that substituent is. So 1, 2, 3, 4, 5, 6. Okay. Now we have our substituent. We have to name our substituent. What's a 2-carbon substituent called? This would be an ethyl group. So this would now, we put it all together. We only have one substituent, so we don't have to worry about the alpha order thing. 1-ethyl cyclohexane. Now, if there's only one substituent on the ring, you can actually drop that one because you're always going to put it at position 1, right? So there's no point in including the 1. If there's more than 1, then I would have to include it. Okay, but when there's 1, you'll commonly see it without that altogether. To be honest, if you put a 1 out front there, that's not the biggest deal in the world to me. But you will see it without any numbering at all, because again, it's just implied that it's at that first position. Okay, but the takeaway is the cyclic alkane, the cycloalkane, is the parent chain automatically. Yeah, so then actually another good example of kind of that same phenomena would be here. If we have a methane, 1 carbon, with a chloro group on it, we don't call it 1 chloromethane, we just call it chloromethane because there's only 1 carbon, right? So again, the numbering doesn't mean anything. It's actually the same thing with bromo, with ethane as well. You know, here, if I were to find my parent chain, that's here. So it becomes an ethane is my parent chain. I have my substituent here. That's a bromo. And then I would number such that I don't really need to include the number because whatever carbon that bromo has on it is just automatically carbon 1. When I get to propane and such, then I do have to include it, right? Because there's 2-fluoropropane, where, again, here's my parent chain. That parent chain is a propane because it's 3 carbons. I go through and number my carbons, 1, 2, 3. I have my substituent, which is fluorine, so it's a fluoro group, and it lives at position 2. I have to put that number in there because there's also 1 fluoropropane, right? So 1 fluoropropane and 2 fluoropropane are different molecules. And then this one you can convince yourself is 2-chloro, 2-methylpropane. These also give you the common names. I'm not going to expect you to have the common names memorized, to be honest. We have to have all those different substituents that I showed you before, the isobutyl and everything. You can see that that's where these names are kind of stem from. We have isopropyl here, Tert butyl here. Truth be told, I would much rather you know how to use the IUPAC naming system. And as soon as you are trying to memorize all the common names as well, it's not really fair in my opinion. What is a common name? Remember, the IUPAC was a group of scientists that got together and decided that this is what we should call things, how we should do this. A common name is something that existed beforehand as a shorthand before, was widely used beforehand. So isopropyl fluoride had been around before the IUPAC came, and so that's why it kind of sticks around. You might find bottles in the stockroom that say isopropyl fluoride instead of 2-fluoropropane, although unless that bottle's really old, now it will say both of those on there. So again, I'm gonna make an executive decision that says, don't worry about these common name here, worry about the IUPAC name. Okay, so now we got to go the other way from name to structure here. We're going to make 2,3-dimethylbutane. So notice that now we have this situation where we have 2 methyl groups. One of them's at position 2 and one of them's at position 3. So the way that we refer to that is as a dimethyl, 2,3-dimethyl. So that di meaning 2 methyl groups. Okay, so 2,3-dimethylbutane. What's our parent chain? It's the butane. So that's what we're going to start with. We're going to go ahead and start with drawing just the parent chain. So drawing those 4 carbons. Okay, if I was going to do this in the bond line instead, do I have that? Oh, I do. Okay. 1, 2, 3, 4 carbons, right? So that's what we're going to do. Then sort of start from the back of the name and then work up. All right, now I'm going to number my carbons because that's how I'm going to know where to put those different groups. Right, I've numbered my carbons, and my substituents are 2,3-dimethyl. That means one of those methyl groups is on carbon 2. That's one methyl group. The other methyl group is on carbon 3. That's my other methyl group. All right, so 2,3-dimethyl. And same thing here in my bond line structure. Kind of even easier, I just draw an extra line in there that represents those carbons, right? So I guess just to be really good here, let's go ahead and color code. Here's my parent chain still. And these are now these 2 substituents that I've added on, these 2 methyl group substituents that I've added on. Okay, so for my bond line structure, I'm actually done. For my condensed structure, I have one more step, which is to go in there and fill in all the missing hydrogens. Okay, but these are the condensed and bond line structure for 2,3-dimethylbutane. Okay, real quick, just to do a related problem, the only thing we're going to have to know are when there's 2 substituents, so for example, dimethyl. The other thing that I could have asked is what about, let's do 2,2,3-trimethylbutane. How would I have to adjust my drawings to account for 2,2,3? Let's actually just do this guy here. It's going to be easiest to add it to this structure. How can I change this pretty easily to make this 2,2,3-trimethylbutane? Again, if I throw my numbering system back on there, this is carbon 1, 2, 3, 4. If it was 2,2,3-trimethyl, then what I would do would be to erase this hydrogen here, because my carbon can't have more than 4 bonds, and stick in another methyl group. And notice how I had to put, it was 2,2,3. I had to indicate the position of both of those methyl groups. Even though they were both on carbon 2, you have to list that twice. So this would be 2,2,3. Let me make that look more normal. 2,2,3-trimethylbutane. Okay. One of the things is you can dream up a whole bunch of complicated molecules. We won't go more than 3, right? So either dimethyl or trimethyl, dibromo or tribromo, difluoro or trifluoro, etc. Okay, but you don't have to worry about 4, 5, 6, etc. All right, we got another one here, 3-bromo, 1-chlorobutane. So again, my parent chain is the butane. So if I'm going to go condensed, bond line, what am I going to do next? Go through a number. Now I'm going to need to stick a bromine on carbon 3 and a chlorine on carbon 1. One thing to just maybe point out is it wouldn't have mattered if I stuck my chlorine on that side. It really doesn't matter. They would be representing the same thing. And then the last step would be to fill in any missing hydrogens. This chlorine has 2 bonds, so it needs 2 more hydrogens, 2 bonds, 2 more hydrogens. This one already has 3 bonds, so it only needs 1. And then this one only has 1 bond, so it needs 3 hydrogens. Okay, so that's kind of a sloppy way of doing those condensed formulas, but in the interest of time here. Okay, so that kind of walks you through that, and then plugging in those hydrogens. All right, so now the last little level of complication here. Up until this point, the ways that the molecules have been drawn have made numbering it really easy. Okay, but there's one last rule that we need to know here. So let's take this example here. My first step is, of course, let me just actually copy and paste. Shrink it down a little bit. So the first step, again, is to find that longest continuous set of carbons. So here we have our 1, 2, 3, 4, 5. Kind of makes it easy when there's only halo substituents instead of alkyl substituents, but yes. So this is our parent chain. Our parent chain is, again, a pentane. Now we have to number the parent chain as step 2. So up until this point, again, it's been drawn in such a way that made the numbering easier. You could always do it just like we read left to right. 1, 2, 3, 4, 5. However, if I did it that way, my chlorine would be on carbon number 4. So we need to update rule 2 because you want to number the parent chain with lowest possible numbering. So what do I mean by that? There's always 2 ways to number your parent chain, either going the normal way forward or going the opposite direction. 1, 2, 3, 4, 5. And you're going to pick which numbering scheme based on whichever one gives the substituent the lowest number. Okay, so if I chose the red numbering scheme, my chlorine would be at position 4. But if I chose the blue numbering scheme, my chlorine would be at position 2. So that's why the blue numbering scheme is correct. We want the lowest possible numbering. Okay, so that's this last level of complication I'm going to throw at you guys, is when you're numbering your parent chain, you actually want to do it 2 different ways. There's only 2 ways to do it. Do it both ways, and then whichever one has the smallest number, that's the correct way to go. Okay, so again, then we have to, so we have our numbering. Now we're going to go ahead and find our substituent. We're going to name that. That substituent is a chloro. And now we got to put it all together. It would be in alphabetical order. There's only 1. So this is 2-chloropentane. And notice each time I'm bringing those together because it's actually all one word at that point. It's not 2-chloro space pentane. It's 2-chloropentane. Okay, but this is the last little complication that I'm going to throw at you guys, is this idea that when you do your numbering scheme, you need to pick the lowest possible numbering. Okay, so this one is actually, or we can go through this. 1, 2, 3, 4, 5. Notice how it wouldn't have mattered if I went 1, 2, 3, 4, 5. That would have been the exact same thing. Either one will give you an equivalent answer. What I can't do is go 1, 2, 3, 4, because that's not the longest possible contiguous set of carbons, right? So I'm going to do it just kind of the normal way that it's drawn, where the zigzag is my parent chain. So again, my parent chain here is a pentane. All right, and then again, we're going to have 2 possible numbering schemes. First, we'll do it the normal way, and then we'll do it the reverse direction. 1, 2, 3, 4. So which numbering scheme here is correct, the red or the blue? Hopefully you guys see that it is the red numbering scheme, because that makes, because I have a 2 in my red numbering scheme compared to my lowest possible number on the blue numbering scheme would have been a 3. So 2 wins. Okay. So now we have to name our substituents. That's this guy here, is a methyl group. And I have this guy here, which is also a methyl group. What do you do when you have two of the same group? Then it becomes dimethyl, right? So instead of saying 2-methyl, 3-methyl pentane, I say, so I don't say 2-methyl, 2-methyl, 3-methyl pentane. This is incorrect. I instead combine them and I say 2,3 dimethyl pentane. All right, so there is your nomenclature of alkanes with alkyl and halo substituents. All right, so we're getting pretty complicated with the nomenclature. Again, this is one of those things I can guarantee you have to practice to get good at. You're not going to know it right off the bat. I have given you a ton of examples in these quizzes, your participation quizzes after these assignments. Please take advantage of those and do those practices. Because once you get it, you'll know it like the back of your hand, and everything else that will happen, all new nomenclature that we learn will come very easily once you have this base, okay?